Up until the early decades of the 20th century, there were two predominant theories about how the atomic nucleus was fundamentally structured to account for its total mass. The first and most popular of the two was one supported heavily by the era's leading chemists, that the nucleus contained extra protons paired with intra-nuclear electrons that canceled out their charge. The second and far less popular theory was that a completely neutral, massive particle existed inside the core, but it was and always would be too elusive to detect or measure. In 1920, Ernest Rutherford tried to find evidence of this neutral particle with the aid of a glass discharge tube. Rutherford sent powerful electrical currents through hydrogen gas, hoping to force an electron and a proton to permanently fuse together. Rutherford tried to observe any unique sparks or radiation that passed from his target to a specialized detector. While taking into account the immense energy required to overcome the quantum forces at play, Rutherford could not detect any discernible neutral radiation, and therefore concluded that this neutron was either a theoretical fantasy or simply too ghost-like for anyone to be able to measure, essentially leaving the debate completely unresolved. This debate would rage on for around another decade, but the first physical evidence of a neutral atomic building block would come in 1930, when a German physicist would make a brilliant experimental observation that would lead to the first calculations of this mystery particle. Walther Bothe was born in Oranienburg, Germany in 1891. Little is known about Bothe's early academic struggles other than the fact that he enrolled in the University of Berlin and took a strong interest in the newly discovered fields of quantum mechanics and radioactivity. His mentor at Berlin was the legendary Max Planck, the father of quantum theory. In fact, Bothe made his key early discoveries while working closely with Geiger, who had invented the famous Geiger counter. Bothe, while working in his lab, also had the job of studying how alpha particles interacted with light elements, and therefore he had the opportunity to pioneer new ways to track nuclear collisions. In 1930, Bothe teamed up with Herbert Becker to bombard a sample of beryllium with alpha particles emitted by polonium. They spent several months there, focusing specifically on the radiation that shot out of the beryllium. After making dozens of experimental runs with their sensors, they noticed something peculiar about this secondary radiation. Bothe had been using electrical counters to measure the penetrating power of the beam, and noticed that when the alpha particles hit the beryllium target, an intensely powerful, uncharged radiation passed easily through thick layers of lead. Bothe and Becker could come to two main conclusions after observing this phenomenon. The first was that the radiation was just ultra-high energy gamma rays, packing far more energy than any natural radioactive process observed before. The second was that the established laws of physics regarding light and energy transfer were somehow incomplete. To try and figure out exactly what this radiation was, Irène and Frédéric Joliot-Curie in Paris began studying the mysterious beryllium beam by placing various materials in its path. Later, in 1931, the Joliot-Curies read their results to the French Academy of Sciences, where they explained them using a groundbreaking new setup. When the mysterious beryllium beam passed through a block of paraffin wax, a material rich in hydrogen, it knocked heavy protons completely out of the wax. The radiation coming from the beryllium would have had to possess an unbelievable amount of momentum to forcefully kick a massive proton out of a molecular bond. So, the Joliot-Curies just needed to calculate how much energy the original beam needed to displace these heavy protons, compared to what was predicted by the standard equations of photon scattering. The Joliot-Curies found this required energy to be absurdly high, roughly 50 million electron volts if the beam was made of massless gamma rays. Combining this with the known rules of momentum, they published their findings, concluding that they had discovered a new type of super gamma ray capable of knocking out atomic cores. This conclusion, however, was conceptually flawed. Most of the error in the French team's assumptions was attributed to two correlated oversights. The first was the belief that only massless light waves could travel freely without leaving an electric trail in their cloud chambers. The second was a reluctance to abandon the established intra-nuclear electron theory, which blinded them to the reality of a completely new particle. The Joliot-Curies published their results in a prominent paper detailing the ejection of protons by mysterious radiation the next year, in early 1932. Just weeks after their work brought to light the first clear evidence of this kinetic force, English physicist James Chadwick refined it even further using an entirely different analytical method, classical collision kinematics. Chadwick's intention was not to discover a new type of light, but rather to find definitive evidence of Rutherford's long-lost neutral particle. Chadwick figured that if he were to measure the exact recoil speeds of different types of gas atoms being hit by the beam, it would mathematically disprove the gamma-ray theory. The Joliot-Curies had only measured hydrogen protons, but a single data point wasn't enough to calculate a definitive mass. Chadwick was able to quickly build an apparatus to blast nitrogen and helium gases, and he noticed a stunning phenomenon: a massive energy transfer that was mathematically impossible for a massless wave. With some genius insight, Chadwick determined that these weird atomic recoils were due to the beryllium radiation actually being a solid, uncharged particle playing subatomic billiards. When a heavy neutral particle hits a light hydrogen atom, the proton shoots forward. When it hits a heavier nitrogen atom, the nitrogen moves slower, but with a specific measurable momentum. The discovery of this kinetic relationship by Chadwick not only provided the first direct evidence that the neutron was real, but also allowed him to calculate its mass through simple algebra quite precisely. He determined that the neutron's mass is approximately 1.006 times that of a proton, which was off by only a fraction of a percent. The evidence provided by Chadwick was crucial in determining that atomic nuclei are made of distinct protons and neutrons. There was still some initial opposition to Chadwick's exact conclusions after his initial publication, led mainly by physicists who still believed the neutron was just a proton and electron tightly bound together. They believed that these weird mass anomalies were due to the nuclear binding energy itself, and not because the neutron was a unique, indivisible particle. Heisenberg had tried to model the atom's structure mathematically using this newly discovered neutron. But when he couldn't reconcile the quantum spin statistics of the nitrogen nucleus, he adopted the independent fundamental particle theory and held it firmly. Later, quantum physicists provided further evidence that Chadwick was correct in his mass calculations, and other physicists who came after him further refined his results. Interestingly enough, at exactly the same time, an Italian theoretical physicist named Ettore Majorana was independently devising a very similar mathematical model, but with some slight differences in how the nuclear forces operated. Majorana's setup also included protons and neutrons, but in his case, the stabilizing force wasn't just electrical, but rather an entirely new, strong force that swapped identities between the particles. The interactions between protons and neutrons allowed the nucleus to stay incredibly stable despite the repulsive electrical forces. Knowing the exchange rate of these forces, physicists were able to calculate nuclear binding energies extremely close to today's accepted values. Most of the measurements of the neutron up to this point have been close to accurate with less than a few % error, but they have not been perfectly precise. Most of the mass values rounded off the subtle mass difference between a proton and a neutron. Unlocking this final decimal point would require observing the neutron completely alone, outside the nucleus. This technology would not come until after World War II, and would come at the hands of experimental physicists studying the beta decay of free neutrons. Arthur Snell and later J.M. Robson are known more famously for their post-war experiments tracking the radioactive decay of isolated neutrons. It is one of the most brilliant precision measurements in particle physics, providing strong evidence that a free neutron is unstable and has a half-life. Robson was a pioneer in precision vacuum instruments and had been brainstorming ideas of how to isolate a neutron beam since the first nuclear reactors were brought online. He started with trying to find ways to extract a pure beam of thermal neutrons from the Chalk River nuclear reactor using massive shielding arrays, and expanding the distance the particles would travel in a vacuum. Still, even with a highly intense nuclear reactor, Robson was initially not satisfied with the background radiation ruining his readings. Several years after his first attempts, in 1950, Robson began planning a new experiment that would measure free neutrons decaying inside a massive, customized vacuum tube spectrometer. Still using the same magnetic separation tactics employed by earlier particle physicists, and with the help of a state-of-the-art electron multiplier, Robson reached a breakthrough value for the half-life of a free neutron, proving it decays into a proton, an electron, and an antineutrino in just over 10 minutes. This still was not the last attempt by the scientific community to refine the calculated mass and lifetime of the neutron further. There were some sources of error with this early reactor experiment. The first was rogue gamma radiation from the core that happened to bypass the lead shielding. This background noise compromised the baseline readings somewhat, and coupled with the blurry energy spectrums caused by residual gas molecules inside the spectrometer, it's understandable that physicists were still not entirely satisfied with their ultimate measurements. The next and final efforts would continue for the rest of the century, and wouldn't reach peak precision until the advent of neutron bottle experiments. For these later attempts, scientists invented a new and incredibly clever device. This device was essentially a magnetic trap chilled to near absolute zero. Perhaps the most impressive aspect of this trap was not its temperature, but the fact that the entire chamber was made to perfectly levitate ultra-cold neutrons using magnetic fields alone. Physicists, frustrated with neutrons crashing into the walls of their instruments in previous years, wanted physical matter to have absolutely no effect whatsoever on their decay measurements. Inside the trap were an array of sensors that monitored the surviving neutrons successively, trapping them for upwards of hundreds of seconds. This setup was able to perfectly isolate the neutron from external forces before it naturally decayed and triggered the detectors. Today's scientists plan continuous series of measurements at modern accelerator facilities to get the most precise standard model parameters they can. These extreme cryogenic systems are not completely immune to error either, as they are still prone to microscopic magnetic fluctuations, which can shift the trapping potential at times. Regardless, the modern results derived from these ultra-cold traps have locked in the neutron mass at 1.00866 atomic mass units and a precise lifespan of about 14 minutes and 39 seconds. It's astounding how well Chadwick's initial collision method worked, and how it was the primary method of calculations up until nuclear reactors and magnetic traps were designed. Today, the exact mass and behavior of the neutron are set as fundamental pillars of quantum chromodynamics, and our understanding of the universe's creation is heavily reliant on the precise fraction of a second a neutron can survive alone. This means that today, measuring the neutron does not just impact the accepted weight of an atom, but rather further refines our understanding of the Big Bang and star formation as more and more precise measurements are made. The neutron is an incredibly stable particle when bound in a nucleus, but when completely isolated, its fragile nature is exposed. It's our universal glue, and understanding its limits is a prime example of pushing nuclear physics to its boundaries. The sheer fact that scientists in the 1930s were able to take what seemed entirely undetectable to them before and turn it into a perfectly quantifiable foundation of matter is beyond remarkable. Thanks to decades of innovation and the relentless work of many brilliant physicists, our understanding of the subatomic world has grown significantly, along with the fundamental forces that hold our universe together. Thank you for watching. This video is brought to you by the Deepstash app. Get smarter every day.
Try it today.